Do you like books? I mean, really, really like books? Then you're in the right place. Each week, your host, Sam Hankin, interviews the best of today's top-selling authors and the up-and-coming superstars of modern literature. This is The Avid Reader. Here is your host, Sam Hankin.
Hi, everyone. Welcome to another edition of The Avid Reader, brought to you by Wellington Square Bookshop. Our guest today is Jim Baggott, co-author of Quantum Drama, From the Bohr-Einstein Debate to the Riddle of Entanglement. It was published in July by the Oxford University Press. Jim's co-author was John Heilbron, who sadly passed away in November. Jim is a writer who studies science and philosophy, science history. He's the author of Farewell to Reality, Origins, and Higgs, the invention and discovery of the God particle. And John was an historian of science. He wrote over 20 books dealing with the history of science, including phenomena such as geometry, electricity, quantum physics, as well as biographies of scientists such as Galileo and Max Planck. And The Sun and the Church, Cathedrals as Solar Observatories, which was kind of off the beaten track, was awarded the profession's highest prize, which was the Pfizer Prize. So their combined work led to this book that John never saw, unfortunately, which is kind of a capstone of their work individually and together. So from the aforementioned debate between Einstein and Bohr, which questioned the very fabric of existence and gave rise to a lot of emotional, intellectual turmoil, for the most part between the two of them, a good-natured one, to the unfathomable, for the layman, me, study of quantum mechanics, this book explores such topics, many of which are familiar to the lay reader as metaphors. Good old Schrodinger, the double-slit experiment, spooky action at a distance, Heisenberg's uncertainty principle, where it is, what is momentum, one or the other, wave duality, wave-particle duality, the Copenhagen school, black body radiation, and so on and so on. There's tons of them. And I know just enough about these subjects to get myself into big trouble. So let's see if we can get more of an understanding of what I'm calling these scientific metaphors, which is as best I can do, as we discuss the topic with Jim. So welcome, Jim. But first, I guess, maybe as an homage to John, how did this book come about, and your partnership as well?
So the thing you have to understand about John, John was the first graduate student of a well-known and highly regarded philosopher of science called Thomas Kuhn at the University of California at Berkeley. And in the very early 60s, joined Kuhn and another historian of science called Paul Foreman on a mission in Copenhagen to begin to capture reflections, document letters, correspondence, papers directly with the folks that actually founded the theory of quantum mechanics in the 1920s. So John sat and spoke with Niels Bohr. He talked to Werner Heisenberg. He talked to Bohr, guy known as Bohr's bulldog, Belgian physicist Leon Rosenfeld, and also Oppenheimer, who happened to be visiting because Bohr died actually shortly after interviewing began in 1962. And Oppenheimer passed through Copenhagen to contribute his own thoughts and recollections to the archive. This archive became known as Sources for the History of Quantum Physics. So John was one of the few left on the planet who actually interacted with the founders of quantum mechanics. And I happened to be sat next to him at dinner following a day's discussion at a meeting in Oxford. And we got on so well that a few days afterwards, I actually suggested a collaboration. I've been fretting about quantum mechanics for about 37 years now, I realize, which is probably not been good for my health. And I would say more than yourself, Sam, I know quite a lot about quantum mechanics, which is just more than enough to get me in a lot of trouble. So it was really a coming together. I had some ambitions to want to try to John would hate these phrases that I'm about to give you, but I was keen to kind of put the record straight. There's been a lot of anti-Bohr and anti-Copenhagen rhetoric spilling into popular science literature for a good many years now. And I was quite keen. My understanding has built slowly, but John was a Bohr expert. He'd studied Bohr for decades, and probably was one again of the few historians on the planet who could actually tell you what Bohr was thinking. Wasn't always very easy because Bohr was inclined to be very obscure in much of his writing and in much of his language. And I was really just keen. For me, it was a culmination of years and years of trying to understand why I couldn't understand quantum mechanics. And for John, I think an opportunity maybe for him to revisit some of the work that he actually began as a graduate student with Thomas Kuhn back in the early 1960s.
You know, it's interesting, as a bookseller, obviously, I'm always interested in the cover and the title, because when this lays on our table, that's what people look at when they come in. And so, you know, you see the two gentlemen, you see the spectrum. It's a great cover and it's a great title. But if you want to talk about, I mean, obviously, because of the title, we're going to be talking about Einstein and Bohr. And they were buddies. It was a very convivial conversation they had over the years, but they had different viewpoints. They kind of looked at the world, a world that had never been seen before, with different colored lenses. So I guess the most important question is, because you guys posed it, what was going on with the two of them?
They were both trained in physics in around, well, during the same era. So both effectively classically trained. And it's actually easily overlooked, but Einstein himself was somewhat enamored of the Austrian physicist Ernst Mach for a while, and the special theory of relativity, which he published in 1905, can be viewed as a very empiricist or positivist theory. It's basically saying our sense of space and time are relative, which is nothing other than basically saying we have to take the world as we experience it, not as we would theoretically conjure images of it in our heads. So it was only later somewhat later in Einstein's life that he became very firmly realist in his outlook. Effectively, I think he accused Ernst Mach of being as good at physics as he was wretched at philosophy. So his opinion of Mach changed over time as he began to understand effectively what the philosophy of positivism was actually denying us access to, which is ever deeper and deeper understanding of the nature of physical reality. Bohr, there's a lot of stuff you'll read, not just in the popular science literature, but also in the academic literature, that Bohr was something of a positivist or an instrumentalist or an empiricist, or pick any phrase you like. But I actually think he was very firmly an objective realist, but he was content with the notion that one can devise a theory that represents reality without describing it in any detailed sense. And so his views, the notion of complementarity, of waves and of particles, and of other types of analogies, he saw as effectively the best that we could do as classical objects, given our size and the way our minds work, with very, very strange and somewhat obscure quantum events that we could watch unfold in the laboratory. And he basically argued that we shouldn't really take this theory too literally. We've got it. It clearly works. But if you take the concepts too literally, you're likely to err. And that I think has actually been proved time and time again. The whole work, as we relate in the book, that led eventually to this thing called Bell's theorem and Bell's inequality, and the idea of entanglement, the idea that there can be correlations, mysterious correlations between particles that are now very distant from one another, having interacted in the past, cannot be explained. We have no rational explanation for that entanglement other than we can see that it exists. And the reason we don't have a rational explanation for it is because quantum mechanics, the theory of quantum mechanics, doesn't give you that explanation. And again, I can hear Bohr in the back of my head saying that's because we're trying to take the theory too literally. You can't expect it to explain the world in the way that you would like to see it explained.
Yeah, like Feynman said, if you think you know, I can honestly say that there is nobody who understands quantum mechanics. But it's funny the way you describe Einstein and his Nobel Prize, I guess in 1921, for the discovery of the photoelectric effect, which actually did lay the foundations to a certain extent for quantum mechanics, which is funny because you said the committee kind of sidestepped.
Yes.
They sidestepped relativity and they awarded it for something that they decided that would be the substitute of the award for relativity. But it actually is so important because it does indeed lay the foundation, right?
Yeah. Yeah, it does, and in fact, much more so. So again, a popular reading of the history of quantum physics would trace the origin of quantum mechanics to Max Planck, who in 1900 effectively deduced that light radiation must be quantized. It must come in packets or bundles of energy that we now call photons today. But in fact, he didn't actually do that. And the person that made that connection, that equated the energy of a photon to its frequency, was actually Einstein in 1905. And again, the logic behind that was the logic that led to the unraveling of the mystery of the photoelectric effect. So when you shine light on a metal surface, light of a certain energy, a certain frequency, will kick out electrons from that surface. But light that isn't of the right frequency, no matter how intense it is, won't work. That has to be a certain frequency, in other words, a certain energy, and that's the connection between the two, to enable the electrons to be liberated from the surface of a metal. And so Einstein was brave or foolhardy enough to want to say maybe light actually does come in these quantized bundles, which we now call photons. And that was seen as being way too radical for the prevailing wisdom of the physics community at the time, which is why his Nobel Prize is carefully worded.
Well, you know, it's funny, and we'll get back to it in a minute, but there's one thing I've always wondered, because Planck's constant and then Einstein cosmological constant, I think as a layperson, everyone thinks it's like fudging. Thing doesn't work out right, so you just stick this in so it works. But then what always gets me, and I wish he was still alive, is Einstein saying the cosmological constant was the biggest blunder of his life. And now with dark energy and dark matter, it turns out, wait a minute, he was 100%. Well, no, I don't know. He seems as if he was right. He would have been vindicated to a certain extent.
Yeah.
So I don't understand. I don't get it.
So absolutely. Sometimes physics works in mysterious ways. In Einstein's case, he introduced the cosmological constant because for him, what he wanted to do was create a static universe. His equations of general relativity suggested, in fact, that the universe might be done. There was nothing to stop the universe expanding or contracting or doing all sorts of different things. And there's an interesting history there, which I actually, funnily enough, tell in my next book, which will be published probably sometime in 2025. I can't give you an exact date yet, but It is quite fascinating. Planck's constant is something a little bit different. Planck's constant is in effect a relationship if you think about it, it's kind of like the gradient of a straight line graph. It's in many ways artificial, which is why many physicists actually formulate their equations where Planck's constant is set equal to 1 and the speed of light is set equal to 1. You can just fiddle around with the units to get those relationships in place. But what effectively it's saying is that there's a direct relationship between energy in quantum mechanics and frequency. Now, whether it's the frequency of a photon or the frequency of an electron, which again was Louis de Broglie's famous breakthrough in 1923, when he said, look, what Einstein has figured out for light, that it might come in packets called photons, might also hold for what we think of as particles called electrons. What if electrons can also be thought of as waves? And that was the thing that really set the whole quantum revolution, gave it a huge impetus.
That leads to what perforce should be our next discussion, which is what lay people probably hear more than, well, there's, you know, the cat and playing dice with the universe and spooky action at a distance are what we all know. But if you talk about the double slit experiment and the idea of back to light as a wave and a particle and the interference pattern, because for the general public, it's seen as basically impossible. And it makes my place in the universe seem a little suspect to me. So if you could explain that, well, can you explain?
Yeah, well, it's interesting because, you know, lay people are not the only ones that are baffled by this. Physicists are baffled by it too. And that is simply because I can write down the equations of quantum mechanics, which can explain how it's possible for us to model or think of or calculate the probability of a single photon finding its way through two slits and impinging on a screen to be detected at the other end. And that probability will say, well, there's a chance it'll hit here, there, everywhere else. But what you'll see in that pattern of probabilities is that they concentrate around what is going to become a bright fringe. And they are very, very low. The probabilities are near zero in what will become a dark fringe. So the interference effect is inherent in the behavior of individual photons somehow, even though quantum mechanics doesn't allow us to predict precisely where the next photon will strike the screen. Take those two slits away or change the two slits for one slit and you'll get a different pattern. I mean, that's just experimental physics. That's what we find. So it's when we try to bring classical preconceptions, like there must be then a single particle called a photon, which somehow finds its way through two slits at once. Can that be right? And then finds its way to the screen. That's when we get into trouble, which was Bohr's whole argument. Don't try to do that. Don't try to visualize it, because if you try to visualize it, you'll tie yourself in knots. Just accept that we have photons on this side, we have a screen on this side, and we've got an equation that allows us to predict where those photons are going to fall.
But then, you know, it's nice that we're serializing the book because it goes this way. If you go to the idea of observer-dependent things, or if you go to Schrodinger's cat and you say, okay, the wave function doesn't collapse until the observer looks at the cat and then it's either alive or dead. And I always think like, okay, doesn't have to be science. I have a friend, Joe Clark. I met him in college. I didn't see him for 30 years. He calls me up. I didn't know whether he was alive or dead. I didn't see him for 30 years. He never responded to my texts. This was before text. Anyway, he calls me up and he goes, do you want to climb Mount Kilimanjaro? And I said, okay, because I would be such a wuss if I said no. So we climbed Mount Kilimanjaro in 2005. And since that point, I've texted him, I've called him, no answer, no response. So as far as I'm concerned, I don't know whether he's alive or dead. And the only time I will know he's alive or dead if someone tells me he died. So that goes back to like, okay, and no scientist has agreed with me on this. Am I living in a solipsistic universe? Because if I don't know whether he's alive or dead, then I'm controlling his state of existence unless there's an independent there's an independent reality. And then you go back to Descartes.
Well, you can have this kind of fun, and I wouldn't want to prevent you from having this kind of fun. I mean, the most recent example in terms of popular culture was the TV adaptation of Blake Crouch's book Dark Matter, which features a multiverse, which features many different versions of a single guy who's figured out how he can navigate his way through different doors which take him to different versions of reality. And that's all great stuff. It's very, very entertaining. But then you've got to bring the thing back down to the physics of every day. Schrodinger, his motivation for devising the parable or the paradox of the cat was to actually say, look, quantum mechanics is absurd, because nowhere in the theory is there a point at which we can definitively say, okay, well, that's where quantum mechanics ends, and this is where classical mechanics takes over. He didn't mean it to be taken literally. And in fact, I think it was Ursula McGinn, I think, was the first in a science fiction story to introduce the notion of Schrodinger's cat as a literary reference, because it's fascinating. But in actual truth, what Bohr was actually saying, just to come back to the point, was that indeed quantum mechanics doesn't tell us where the quantum world ends and the classical world takes over. But what he did argue was that later on in the 50s, I think he wrote a series of essays, a couple of which make reference to what Bohr called the irreversible act of amplification. So if you want to look at where that transition takes place, it almost certainly takes place as quantum events get amplified up, get blown up to become a signal of some description, maybe the deflection of a pointer on a gauge, maybe a light bulb goes off. However it's manifested, by the time you get to that, you are in the classical world, and there's no mysterious, parallel world where the light didn't go on or the needle didn't move on the gauge. In effect, somewhere in that process, from going from the very small up to the scale where we can perceive it and make a note in our laboratory notebook, the quantum weirdness has gone, in a sense. Or the description that we use more correctly, where we talk about superpositions, it's both on or off, or it's up or down, that kind of device that we use to try to calculate quantum probabilities is no longer relevant by the time the signal is amplified up to classical scales. And that was Bohr's contention, although he never had obviously any physical evidence to show that was indeed where the transition takes place. Nowadays, physicists talk about the notion of decoherence. So they basically argue that, in effect, what happens is the transition from quantum to classical takes place because, in effect, the wave function becomes incoherent, I want to say, but it's decoherent. And so we lose the superposition, the on or off or up or down. And that happens long before we get to the cat. So the cat is fine. It is literally either dead in the box before we lift the lid and look, or it's alive in the box before we lift the lid and look.
Well, it's like, you got to give me kind of a break, because what I'm always reading is what comes down through the newspaper. Scientists discover the origins of dark matter. And the thing about it is like Schrodinger, the idea is, this is kind of ridiculous, this experiment, this metaphor, this analog. It's like when Fred Hoyle made fun of the idea of Big Bang.
Yes.
Big Bang is, much to his chagrin, perhaps.
Yes.
We all believe in. I mean, there's nobody that doesn't believe in the Big Bang now.
That's not true. That's actually not true.
Well, no, you're right. Yeah. But
no, I follow a group of cosmologists who have an online forum who are very, very much anti-Big Bang.
Right.
And I use them because they're a good source of updated information. If some scientist posts something on the archive, the latest findings from the James Webb Space Telescope, for example, these are the guys that are quickly, downloading it and looking at it. So I'm part of this group just as an observer. So I get to find out when this stuff's going on. So they do exist.
Yeah, and I just forgot it because I read science fiction, so obviously I should know about white holes, and I should know about the idea that time and space didn't exist before the Big Bang. Okay, so if we keep going with the book, and the good thing about the book is you can read it as a layman and has a great index and notes, but you only put in formulas when you have to put in formulas, which is really good for the reader. But so that led me to where you don't really have to have formulas is if you describe to me the Copenhagen school. So that's something that people have heard the term or heard the word Copenhagen. So what exactly is that, and why is that completely different than Einstein's position?
Well, so Einstein, it's very, very difficult to give you a very simple answer to that without moving to not caricatures exactly, but giving you a sketch that isn't completely the whole story. So forgive me for doing that,
No, I
because
appreciate
that's what I'm about to do.
No, I appreciate
But in essence, Einstein believed that the purpose of science was to get to a description, an understanding of reality. This is a reality that exists independently of anyone thinking about it. It exists independently of the existence of humankind. It's a description of what's going on in the universe, whether we are here to see it or not. Bohr wouldn't necessarily have argued against any of that, but what he said is in quantum mechanics, we've hit the buffers. This is no longer giving us a description or an understanding of some kind of reality beneath the equations. We're having to settle for the equations, and all the equations can do is allow us to calculate probabilities. And that, in essence, is the Copenhagen interpretation. That it's quantum mechanics is a theory that is meant to be that it is symbolic. It deals with probabilities. Get used to that. It isn't to be taken too literally, so don't overinterpret this thing called the wave function. It doesn't really exist as a physical thing. It's a shorthand. It allows us, it's a vehicle, if you like, an instrument that allows us to get from one set of facts to predict another set of facts. And if you try and interpret it beyond that, you'll run into difficulties. Now, Einstein said, well, why should we settle for that? Surely that we've stopped too soon. Why stop there? Why not push and try and get hold of a theory that does give us a little bit more insight, a little bit more understanding of the nature of reality. Now, again, I want to be absolutely clear. The Copenhagen interpretation doesn't say electrons don't exist until we look at them. That's absurd. That's ridiculous. What it is saying is you can't even tell what an electron is. It exists, but you can't tell what it is until we look at it.
But Einstein takes a walk and he says to his buddy,
"Yeah,
you're telling me that if I don't look at the moon, it's not up there."
Yeah, and that's clearly,
That's
and the reason he says that is because that is, of course, ridiculous. Of course, the moon is there when nobody looks at it or thinks about it. And Bohr is saying, but of course, an electron is there whether nobody looks at it or thinks about it. But you cannot say anything about it until you look.
But you say, of course.
You cannot say whether it's a
how can science say, of course? You're saying, of course, the moon is still there.
Yeah.
It might not be. The sun might not rise.
No. I say that because I am a realist. Okay. If I were an empiricist or a positivist, I'd say, well, yeah, but you have to go on the basis of what you can see. And yes, for as long as I see it, the moon exists. But I don't know what happens to it when I don't look. But I assume it's still there, just like I assume the sun's going to rise in the morning, just like I assume that there will be an election in the US in November. So I assume that these things, and that actually paints my portrait as having a particular philosophy of science, which is that of a realist. However, Bohr is saying in quantum mechanics, we've hit a limit, and it's dangerous to try and push quantum mechanics beyond to try and tell us something that we can't actually get a grip on, and that is what happens at this subatomic level, at the level of electrons and photons, without reference to some kind of apparatus, some kind of measurement that's going to tell us what it is that we're looking at.
Yeah.
Now, does it exist? Yes, it exists. What does it look like before we look? Nobody knows.
Yeah, but that's what that's the pablum that's fed to the public is not that at all, and that's why the public doesn't. But you can't, because they're not smart enough. But when I was a little kid, I thought that my parents took the universe apart when I went to sleep, because there wasn't any reason to have it. You know, I kept thinking this is a lot of hard work they got to do every night, because they have to put it together again in the morning.
They'd have to employ a lot of people.
I assumed that that's what happened. I made that assumption. What about okay, let's take the many worlds interpretation.
No, so I haven't quite answered your question. So,
okay, go ahead.
So
sorry,
that was what you asked about, specifically about the Copenhagen school.
Right.
Here we have a real problem, because in the end, those physicists I can name that belonged to the Copenhagen school all had slightly different interpretations of what they thought they were talking about when they talked about. In fact, it was Heisenberg who invented the term Copenhagen interpretation, and he didn't do that until the 1950s. So there was no Copenhagen interpretation, arguably, in the late 1920s, 30s, when Einstein and Bohr were having their debate. So a lot of this stuff, and again, so we come back to my ambitions for the book and the collaboration with John, was to try and get a handle on the history and say, look, this is, as far as we can tell, from archives, from correspondence, from writings, from lectures, as far as we can tell, this is the way it was. Now, history can be complicated. Sometimes we want to simplify it, make it simple, make it easier to deal with, make it easier to understand. And that means we use caricatures. Bohr becomes a bit of an evil spirit, dominating poor old Einstein, who is going senile, and there's a ding dong, and Bohr wins the debate. And of course, we all obey Bohr now. And again, there's this view that the Copenhagen interpretation dominated quantum physics, and no one could raise a hand and say, but I don't agree, because that was, you know, Bohr's will was paramount. But in actual fact, if you again look at what actually happened in history, after the end of the Second World War, American physics dominated physics. And within the context of American physics, there was actually no appetite for any kind of philosophical debate. You know, these were the folks that had built the bomb, the atom bomb. Let's just overlook, we had all these Europeans at Los Alamos also contributing to the Manhattan Project, but basically it was an American, a wonder of American science. And as a consequence of that Americanization of physics, philosophical arguments about whether the wave function should be interpreted differently became kind of uninteresting. They became irrelevant. If you wanted to get on with a physics career, you didn't waste your time with that stuff. And that's where this notion of shut up and calculate actually came from. A guy called David Mermin coined it, but effectively it was a view that was coming from his professors at Harvard, who said, look, you don't waste your time on that stuff. If you want to make a valid contribution to the future of physics, think of work on something else. So the Copenhagen school was not a uniform body. These were not all priests arguing the same mantra, the same Bohrian mantra. They all had different views, which makes it complicated. Heisenberg was more of a positivist than Bohr ever was. And so you get this mess that is difficult to make a lot of sense of. But that was the history as far as we can ascertain it. And you also had other forces at play, which I find absolutely fascinating. So the embrace of the notion of acausality or indeterminism was positively seized by physicists in Europe, particularly German physicists, because of the political circumstances in the Weimar Republic at the time. The whole communist philosophy is based on Marxist materialism. And so the Copenhagen interpretation, because it was anti-materialist, was just not going to wash in the Soviet Union. And so you had these hugely massive political forces that were, of course, about to spill into World War, at a time when people were trying to stubbornly try and work out what the hell this quantum mechanics was all about.
It was cool the way you talked about the political implications. Jewish science or Heisenberg they could have gotten the bomb before us, but not. I keep pushing this point because it's interesting to me, fascinating to me, and I wake up in the morning thinking about this stuff. But it's like Bertrand Russell and Lord Alfred Whitehead, they do this Principia Mathematica and they think, eureka, this is the entire, we've done it. And Bertrand Russell said it broke his brain. And then Kurt Gödel says, no, you really messed up big time. This whole thing is totally worthless. And then, okay, take what we get as laymen, and you haven't lost sight of that. And you said it at the beginning, but say, take Hilbert's Hotel, you got this infinite hotel where they just move everybody one room over. So people think, I think that's real. I think Hilbert's Hotel is real. And this is what actually exists. And I think you're trying to tell me, no, it doesn't. This is just something we're throwing out there, but it's not like it really is.
Yes. Yeah, and you can accuse physicists, scientists generally of being misleading, but what they're all trying to do is, first of all, they're posing puzzles for themselves. So Schrodinger's cat was never intended to be a popular metaphor. It never a cultural icon that it has become.
What did it was not at a dinner party? Did he write it down? Was it just a joke he made to his friend?
It's one paragraph in a 3-part article written in German and published in 1935, around the time of Einstein, Podolsky, Rosen. So you had this he's aiming his argument at other physicists, saying, look guys, this is ridiculous. Quantum mechanics can't be right, because look at this cat. And then suddenly in the 1970s, it gets snatched and it becomes part of the iconography. I like to think there's a mythology around quantum mechanics. This is why I dearly love working with John so much. John was one of his career missions, I think, was debunking certain scientific myths. There's a whole scientific mythology around Galileo that scientists love to promote, but again, it's not based on the historical record. Well, I would say historical truth. Well, John would say there's no such thing. It doesn't exist. And so John argued quite cogently that the whole thing with the scientific myth, and I think to a certain extent the Copenhagen interpretation and what we tend to think of it in popular literature, I think of it as a myth, but myths have a grain of truth, and sometimes a myth can be very important in science because it promotes more effort. And this notion that somehow the Copenhagen interpretation, excuse me, held some kind of dogmatic sway over the entire physics community was certainly motivation for John Bell, certainly motivation for David Bohm, as these guys wrestled with what they thought was an orthodoxy and said, look, we can unstitch this. We can find another way of describing the world that doesn't rely on symbols and denies that there's any further insight to be gained. And in putting in the effort to try and show that there's another way, or there's a possibility that quantum mechanics is in some way wrong or limited, led to experiments in the 1970s and 1980s and continuing to this day, which have revealed the existence of this thing called quantum entanglement, have opened up the possibility of quantum computing, and led, as we now know, to the award of the 2022 Nobel Prizes to Alan Aspect, John Clauser, and Anton Zeilinger for their work in exploring the possibilities that David Bohm and John Bell had exposed.
The most reassuring thing, since you mentioned Galileo, is that Galileo finds comfort with the absurd and the ambiguous, because that gives me a way out. I mean, I can be laying back on this comfortable sofa, happy that I don't know anything, happy that Richard Feynman admits that I don't know anything. But then you have all these guys that come up with string theory, which is non-disprovable. But do you still consider that science? Because
you're asking the wrong guy, I'm afraid.
Well, I'm the wrong guy too.
No. So you mentioned my book, Farewell to Reality, and then that is a whole argument against string theory and multiverse theories, because a threshold at some stage you have to try and draw a line. I think scientific theories, I'm fine. Go work on whatever tickles your fancy. Go and work on whatever absurd notion you can concoct, no problem. If you can get funding for it, go do it. However, a point has to come where you need to, if it's going to be called physics, you need to find ways in which you're going to connect your theoretical structure with reality, with what I call empirical reality, with some facts. You're going to have to find some physical facts that either support or refute the theory. But either way, doesn't matter. Find a way to test it. And string theory has been going for 50, 60 years now, and it shows absolutely no signs of connecting. And I don't have a problem with that either, funnily enough, even though there might be, sources, significant sources of funding put into what I think is possibly a blind alley. What I then start to get a bit worked up about is physicists who arguably should know better than going out and selling the string theory program as the answer to all of our outstanding problems. Right, it explains dark matter, or it could unify quantum mechanics and gravitational theory. It can do all of this, and of course it's done nothing of the kind. So I don't enjoy the hype that tends to go with the string theory program. I'm not against the idea of anyone wanting to spend time working on it if they can get funding.
Yeah, but it's like light bending. I mean, Einstein posits it, and either believe it or not, you're ridiculed or you're admired. And then you take a ship and you go to the eclipse. It's a really cloudy day. And then you take all these plates, and then for 5 minutes, it clears up and you get these plates that might, but string theory, you've said this in your book, what you might consider completely wrong now may be right in the future. Suppose eventually there's experiments that actually can prove that. You're discounting that completely. You're saying that
no, I'm not discounting it. I'm saying, scientists should work on whatever intrigues them and they can get funding for. What I don't enjoy is misselling the promise of the program in a potentially misleading way. And there have been lots of popular books. I'm not going to name the titles or the authors. Lots of popular books extolling the merits of string theory, and all that these books present are theoretical structures with no foundation or the promise of ever connecting with physical reality. Now, of course, that could all change in 10 years, 50 years time. How patient are we going to be? I don't mind, and I don't care, to be perfectly honest. what I would quite like in science is some honesty and integrity. So when you say, well, we've got this fantastic idea, it's called string theory. Yeah, but we don't know if it's true. One of my favorite examples of the kind of honesty that I'm talking about is there was a book published a few years ago. I'm sorry, I'm going to forget the name of the author, and the book title is Why String Theory? And there's a chapter 7, let's say, and it says experimental evidence for string theory. And you turn to chapter 7, and there's a single sentence in this chapter: there is no experimental evidence for string theory. And that's it.
And there may be sometime in the future. I understand. I agree with you. But then again, it's like cold fusion, perpetual motion. But then you take something like squaring the circle. For a long time, people thought, until it was proven that you couldn't, people thought you actually could square the circle. That's where my brain starts to hurt too. This is
yes,
because all these scientists, we can, it can be done. We can do it to 3 decimals, so why can't we do it to however many decimals? But then someone proves that it can't be done.
Yes.
Which really isn't a question. But do you understand? I mean, you're pretending like you don't know that much, but you do, and I'm asking you for some kinds of answers that will reassure me, and I don't think you can give them to me.
It depends on answers to what. I mean, if you want the answers to life, the universe, and everything, I'm just going to tell you 42, and
I knew
that'll be that. But you knew that already. No, so it's interesting, the journey that I've been on. I've said I've been looking at this now for 37 years, and you'd think I'd figured it out by now. I actually have reached an understanding of why I don't understand quantum mechanics. And I'm going to have to take that as a win, I'm afraid. But in that journey, I've become much more respectful of Niels Bohr and what passes roughly for the Copenhagen view or the Copenhagen interpretation. That doesn't mean to say I agree with it, but I've become more respectful of it. I can understand why it exists. I can understand why Bohr said and wrote what he did. And there's a lot that it should be causing anyone who looks at quantum mechanics to sit back and think, okay, what do I expect to find? What do I expect to get from nature? When I'm now exploring the inside of an atom or the inside of an atomic nucleus even, how can I expect that the things that are going on around me, I would expect to see mirrored or manifested in the internal workings of these things? And the simple answer is you can't expect that. You don't really know what you're going to find. All you can do is you can bring the metaphors or the models that you take from your experience and try to apply them as best you can to what you find inside an atom or inside an atomic nucleus. And that's what physicists do.
You wrote an entire book about Higgs, and I remember, it took him, I don't know, 3 decades, 4 decades to be vindicated. And I remember him sitting
50 years.
And I remember him sitting in the audience at CERN and crying.
Yes.
And I can almost cry just thinking about it. And yet, as the public, all we can think of is this, there's this field, and we think of field in a different sense. I can see it now. There's this field, and somehow the Higgs boson, and you think of it as a boson on a ship. That's the way I think of it, which is not the right way to think of it. That this boson leads everything in a certain way. And we've been told all that time that it's the God particle. We've been told that. So that's what we know. We know it's the God particle. We know it was discovered. We know Higgs was located, but that's all we know.
Yeah. So again, just to backfill on the history, the existence of the Higgs field was arguably known in the 1970s, as soon as Steven Weinberg used the Higgs mechanism in a paper that was called The Theory of Leptons. Now, leptons are electrons and other particles, but basically electrons, and it's the heavier members of the electron family, if you want to think about it that way. And he successfully predicted the masses of other particles called W and Z particles. If you're American, you'll call it Z, W and Z. And these particles were discovered at CERN in the 1980s. So there's a history here. There was an expectation, okay, well, that mechanism has worked. Therefore, that mechanism must apply at higher energies, which would then reveal the fundamental particle of the Higgs field, which is the Higgs boson. And it's called a boson because it has certain properties as a particle. It spins a certain way, whereas electrons spin a different way, and they're called they're called fermions instead of bosons. But you know, that's semantics. That's just physicists labeling things on the basis of what they see. But you know, long before the search began, it was understood that if the Higgs mechanism is correct, the Higgs field must exist, and if the Higgs field must exist, then the Higgs particle must exist. And it was only given the name the God particle because of an American high energy physicist called Leon Lederman, who actually wanted to call it the goddamn particle. Because he said, look, if the universe is the answer, if the universe is the answer, what's the question? And he wanted to call it the goddamn particle because it was proving so very elusive to find. And in the end, the publisher said, no, you can't call it the goddamn particle, so we'll call it the God particle. And that's how it came into being. And that was a book published, I think, in the, if I'm not mistaken, late 80s or early 90s.
I remember buying it. Well, another one that, and I think it's instructive in this interview and for people who read the book, that there are these terms that are given to us, but we don't know unless we know mathematics. You know, as Einstein said, if you don't know mathematics, you're not going to understand the universe. Sorry. But so if you talk about quantum tunneling, for example, as a layman, I'm thinking of tunneling. I'm thinking of someone building a tunnel.
Sure.
I'm thinking of something going through something to get out the other side.
Sure.
Why am I wrong? Where does the metaphor break down?
So again, tunneling is a well-recognized phenomenon. But it goes back to the mystery that we were talking about just a little while ago, and that's the kind of two-slit experiment where you see two-slit interference. So how does one particle at a time go through both slits at once? That seems like an absurd thing. And that's only because you think of particles as self-contained little ball bearings. Whereas, again, if you listen to Bohr, we don't know what these particles, I just did fright quotes then, which if you're listening to this on a podcast, you won't have seen. You know, we think of them as particles because, again, we bring our classical intuition. We think of tennis balls or ball bearings or some little thing with mass. Whereas in quantum mechanics, you actually don't know what these things are until you poke them and prod them and you reveal a certain type of behavior. Oh, okay, well, in this experiment, the electron's behaving like a particle. And in this experiment, it's behaving like a wave. And in quantum tunneling, in effect, that mysterious thing that's not a ball bearing is finding its way through what's known as a potential energy barrier. In other words, it shouldn't be able to go through, but again, only if you think of it as a ball bearing that has to literally tunnel underneath the fence. It's getting on the other side of the fence because, frankly, again, we don't know what it is. And what we can do, though, is calculate the probability, and we find there's a probability of it being on this side of the fence, but there's also this little probability of it being on the other side of the fence. How did it get there? Nobody knows. So you have this notion then, okay, well, so it's tunneled its way through the fence, the potential energy barrier. and mysteriously appeared on the other side. So again, these things are mind-bending to contemplate. They are not mind-bending for physicists who deal with them every day, because they've stopped thinking about them, and they've stopped thinking about them like little ball bearings tunneling under the fence. They just look at the equations and they just do the calculations, and they say, well, hey, you know, there's a probability of it being there, and therefore there it is.
And the problem is for the general public, tunneling implies, because it's a verb, it implies space and time. And when I was a kid, and you and I both, we took science, and that's all it was called, was science. Sure. And you had a solar system of the way an atom worked. And it was very comforting to me, because
yes,
this is what it was. Now all it is, it's even more, I could call it a cloud, I could call it a haze, I could call it a fog. And those are all metaphors that would work to a certain extent, but where, see, you can't tell me unless you give me a formula. That's exactly what you're saying.
No. I again, all I can tell you is there are all of these different ways of looking at it. I learned. You remind me actually of a question I was asked in a tutorial when I was an undergraduate student in Manchester. I won't tell you how many years ago, but a long time ago. And in fact, the lecturer was asking the question to a small group. I think there were 4 or 5 of us in the tutorial. We have this old picture that you would probably find in some old textbooks. The idea that chemical bonds are formed with little hooks and eyes. So you get one atom connected to another atom with a kind of hook and eye, and that's the chemical bond that forms between them. And he was basically, you know, so what's wrong with this picture? Why, you know, what's wrong with it? And I said, well, there's actually nothing wrong with it in principle, if that's all you need to understand bonding. But if there's another aspect of chemical bonding that you need, that this is at a deeper level, then this clearly, the hook and spring thing won't work. And he told me I was right, so therefore I must have been right. So whatever model works to explain a certain phenomenon, it means you're a winner. You've scored. That's fine. The minute you find something further that you can't explain with that model, that's the time when you need another model, or you need to shape your model in a different way, or you need to give it some nuance, or you need to give it another dimension, or you need to do something basically that allows you to go to a deeper level of explanation to explain this other phenomenon that you've uncovered. And that's the way effectively that science progresses. We haven't stopped using Newton's equations, you know, from 2 centuries ago, because they work perfectly well in what we call a classical physical environment. We can put men on the moon using arguably Newtonian physics, no problem. But the minute you want to try and understand how your barcode reader works in the supermarket is the minute you realize Newtonian physics isn't going to help you.
Yeah, and the best way I've found to understand it in terms of Einstein, well, by the way, that question was asked to you approximately 49 years ago.
Thank you.
But anyway, is GPSs. I can't believe they actually have to adjust GPSs to account for relativity.
Yes.
That's amazing.
Well, again, I've written about this in a number of different places, and I've actually had pushback from professional physicists saying, no, that's not true. And so you read some physicists which say, no, that's true. And you read some other physicists which say, well, no, that's not true. But in fact, GPS satellites, they carry an atomic clock. So very, very accurate clocks. And if you want to use Google Maps to find the location of the bar where you're meeting your friends on a Saturday evening, you do have to account for the fact that the satellite is quite high up in the atmosphere and moving quite quickly. So these corrections are, in my view, necessary. In fact, I think I saw a paper that I quoted from that calculated that without these corrections, you'd very soon accumulate errors that could lead you to being 11 kilometers off
So
your target.
how
So
can
if you're looking for the pub where you're going to meet your friends at night and you're 11 kilometers away, I'm afraid you're not going to have a very successful evening.
no, sometimes it's nice to get lost, but oh, well, that's what physics is about too. But how can physicists disagree with that? Because in actuality, it's reality.
Again, I think there's again the possibility of misconception, which has a different and a darker dimension. So there's this misconception, I think, sometimes that um, even what I would call mainstream science, so widely accepted scientific principles, there's a misconception that therefore every scientist buys into these principles. And it's actually never been true. You'll always find a group of radicals somewhere out on the fringes. So there are evolution deniers that are professors in universities in the States, for example, who argue in favor of intelligent design. So you've got this, and you have to a certain extent, that's a consequence of academic freedom. You have those that can get the funding should be allowed to pursue their interests in whatever direction, arguably within some ethical and moral boundaries, wherever it takes them. And as soon as you allow that, you will allow these fringe elements, these fringe scientists to appear, who will argue against, the main body of principles that are accepted almost, but not quite universally.
Well, let me give
And
you
that's how science works.
yeah, but let me give you a spectrum. There are no scientists who believe in a flat Earth, right?
As far as I'm aware.
But the middle ground between flat Earth and intelligent design would be something like, say, cold fusion.
For me, cold fusion was a spurious idea based on erroneous experimental results, and was never any more than that. I understand. I haven't studied it in any real depth, but there might indeed be a bit of a conspiracy around cold fusion, that somehow it really does exist and we're all being denied access to it by the oil companies, or however it might work. But for me as a scientist, cold fusion was based. It was Pons and Fleischmann produced a paper or a couple of papers that actually had erroneous experimental results, and no one could reproduce them. So again, science works by reproducibility as well. You produce something unusual in a lab report and a paper, and then, okay, well, that's interesting. Let's see if we can reproduce those results. And what you find is that if it takes 2 or 3 groups and no one can reproduce the results, the chances are that they're erroneous. Look at the damage that was done by the claim that the MMR vaccine leads to autism in young children. Incredible damage was done, and it took 10 years for the medical profession to reject that claim effectively as spurious and not founded in evidence.
And the same thing happening in America.
And enormous damage was done in the meantime.
Look how much damage can be done if Robert F. Kennedy Jr. is made Secretary of Health in the United States. Holy mackerel. Well, anyway, so
there's aspects of current American politics I really don't like to think about.
Because it could lead to Armageddon, or that America would become a country like Venezuela. Yeah, we're pretty damn close. Okay, you said at the beginning that we could talk till Saturday, but we've been talking over. So the last question I'm going to ask, which is a serious question. If John were here in this third panel next to us, I wish he was. What would he have thought of this conversation? Would he have thought I was a nitwit?
No. John was so this won't help again your podcast listeners, but I have a Substack. It's called Interpretations, and I posted shortly after his death. I posted an essay in his memory. It's not an obituary of John. I did write an obituary. It was published in a UK newspaper called The Guardian.
I read it.
But, I wrote a very personal essay. If you got the time, go have a look at that. Go and search it out and have a look at it. The thing that I found most wonderful in my collaboration with John was how warm and generous he was as a person. In terms of academic achievement, he was godlike as far as I was concerned. I just felt enormous privilege getting the chance to work with him on this. And yet, in our first email exchanges after I broached the idea, he came back to me and he said, actually, the privilege would be all mine. And at no stage in our collaboration did I feel anything other than genuine equal with John in working on this book, even though I mean, as a scholar, he was streets ahead. And I have to say, I taught him a few things as well as he taught me a few things, and our collaboration was humorous. It was generous. It was I couldn't have asked for a better experience in many ways. And I wish he was here. I wish he could have been here to have held the book in his hands, have witnessed, seen the reviews that have come out, and it would have been lovely to have celebrated publication with him. But he was 89 when he passed. He'd had a very, very successful career. Yeah, wherever you are, John.
Yeah, and
thanks for the memory and good luck.
He knew the people on whose shoulders you stand on too.
Correct.
He's amazing. In any event, that's a good way to end. Thank you so much, Tim. I really enjoyed this, and I hope I didn't, I came to you as, like I said, as a layman. And I hope I didn't ask questions that seem silly or I don't know. I hope that I asked questions that you enjoyed answering. I'm a popular science writer, so as far as I'm concerned, there are no silly questions. There are genuine questions born of curiosity, and I'm hoping that I've been able to at least answer some of them in a way that made some sense. Yeah, very well. And hopefully, when your new book comes out, let's talk again.
Yes. So that you know where exactly we are with it. At the moment, it's tentatively called Discordance. It's a history, the troubled history of the Hubble constant. So it's a tour of astronomy, astrophysics, and cosmology from about 1912 to the present day, literally the present day.
Look forward to it.
Okay.
See you again, Jim.
And thanks very much for the invite. Take care.